Somewhere in a lab in Texas, a team of scientists did something that sounds almost impossible. They trained bacteria to build a material stronger than steel, and they did it using nothing but sugar, water, and patience. No oil, no factory smoke, no toxic chemicals. Just living organisms growing in a specific direction on command. Before we get into how they pulled this off, let's talk about the problem they were trying to solve, because the scale of it is honestly hard to wrap your head around. The world now produces more than 430 million tons of plastic every single year. If you try to weigh that number against something familiar, it would be like putting more than 200 fully loaded aircraft carriers on a scale every 12 months. Forever. And here's the part that should really bother you. Out of every ton of plastic ever created since the 1950s, less than 10% has ever been recycled. The rest is either sitting in a landfill, floating somewhere in the ocean, or breaking apart into pieces so small they've started showing up inside human blood, lungs, and even brain tissue. A material humanity invented barely 100 years ago is now something we carry around inside our own bodies without ever agreeing to it. If you're someone who likes watching the quiet moments in science before they turn into headlines, hit the like button now. It genuinely helps this channel keep making videos like this one, and if you subscribe, you won't miss the next story. Now here's the strange part. Everyone agrees plastic is a problem. Governments have talked about it for decades. Countries have signed agreements about it. And yet nothing has actually replaced it. Because replacing plastic turns out to be one of the hardest engineering problems on the planet. Asterisk, asterisk, why plastic never left. Asterisk, asterisk, plastic isn't popular because people love it. It's popular because nothing else does what it does at the price it does it for. It can be melted into any shape, from a syringe to a car bumper. It doesn't rust like metal or rot like wood. It keeps food fresh for weeks, keeps medical tools sterile, keeps water out of places water shouldn't be. Hospitals depend on it. Food supply chains depend on it. Entire industries were built assuming plastic would always be there, cheap and reliable. But the same trait that makes plastic useful is the trait that makes it dangerous. It doesn't disappear. A plastic fork made today could still exist in some form 500 years from now, slowly breaking into smaller and smaller fragments instead of actually going away. Those fragments are now turning up in rivers, in soil, in fish, in birds, and in us. Scientists still don't fully understand what decades of microplastic exposure will do to the human body. And that uncertainty is exactly what makes this urgent. For years, researchers tried to build a replacement corn-based plastics, sugar-based plastics, bacteria-grown plastics that only work in expensive lab conditions. Every single one hit the same wall. You could make something strong, or something that breaks down naturally, or something cheap to produce, but never all three at once. It was like trying to build a car that's fast, safe, and free. Pick to take corn-based plastic, one of the most common alternatives on the market. It only breaks down properly inside an industrial composting facility that holds it above roughly 58 degrees Celsius for weeks. Toss it in your backyard or a regular landfill instead, and it behaves almost exactly like the plastic it was supposed to replace. It also cracks easily, can't handle much heat, and is grown on farmland that could otherwise be feeding people. Then there's a bacteria-based alternative called PHA, which does break down more easily in nature. But the production process is so complex and slow that it costs several times more than regular plastic to manufacture. When something costs 4 or 5 times more than what it's replacing, most companies simply won't touch it. No matter how good the environmental story sounds, for 2 decades that was the ceiling. Nobody could combine real strength, real biodegradability, and a production process that could actually scale that wall is exactly what a team of American researchers just walked straight through. Asterisk, asterisk, a different kind of lab. Asterisk, asterisk, the breakthrough didn't come from a giant oil company or a Silicon Valley startup chasing a trend. It came from a partnership between Rice University and the University of Houston, led by a mechanical and aerospace engineering professor named Mohammad Maqsood Rahman, working alongside a doctoral researcher named Masr Sadi. Their focus wasn't plastic chemistry in the traditional sense. Their focus was bacteria. Specifically, a type of bacteria that naturally produces something called bacterial cellulose. Cellulose itself isn't new. It's the same structural material found in the walls of plant cells, the thing that gives wood its strength and cotton its fiber. Bacteria can produce a purer, more refined version of it, and scientists have known this for years. The problem was always the same one plaguing every other biomaterial. Left alone, the bacteria grow in random tangled directions, like a bowl of spaghetti with no structure. Random growth means weak material. You can't build a phone case, let alone a car panel, out of something with the structural integrity of wet paper. So the Houston and Rice team asked a very specific question. What if you didn't let the bacteria grow randomly? What if you could physically guide them, direct their motion, and force them to build in one organized direction? The same way steel gets stronger when its molecules are aligned instead of scattered. To test that idea, they built something called a rotational bioreactor. Picture a spinning chamber that creates a very specific controlled flow of liquid inside it. As the cellulose-producing bacteria sit inside that chamber, the current gently pushes and guides their movement. Instead of drifting wherever they want, the bacteria are nudged into growing along a single, consistent direction. Sadi described it almost like training a group of workers. Instead of letting them wander around a construction site, doing whatever they feel like, you line them up and have them build in formation. The result of that alignment is where things get genuinely wild. Asterisk, the numbers that made researchers pay attention. Asterisk, asterisk, when the bacteria grew in that aligned, disciplined pattern. The resulting cellulose sheets tested at a tensile strength of up to 436 megapascals. For context, that's already stronger than many types of plastic used in everyday products, and it starts creeping into territory normally reserved for certain metals and glasses. Then the team pushed further. They added something called boron nitride nanosheets into the growth process, essentially feeding the bacteria a nanoscale reinforcement material while they built. The hybrid material that came out the other end tested at roughly 553 megapascals. That's a jump most material scientists don't expect to see from something grown by living organisms in water at room temperature, using no industrial heat and no petroleum at any stage of the process. The strength wasn't the only surprise. The reinforced material also dissipated heat about 3 times faster than the unmodified version, which matters enormously for anything involving electronics, batteries, or components that need to shed heat instead of trapping it. On top of that, the material stayed flexible and foldable, rather than becoming brittle, which is usually the trade-off you make when you push a material's strength this high. Put plainly, this is a material description that used to sound like science fiction. Strong like a metal, flexible like a plastic, transparent in some forms, biodegradable at its core, because it's built entirely from a natural biopolymer instead of fossil fuel derivatives. The team published their full findings in Nature Communications in mid-2025, laying out every measurement openly for the scientific community to check and challenge, which is exactly how a discovery earns credibility instead of hype. Asterisk, why this matters beyond the lab, asterisk, asterisk. Here's the detail that separates this from 100 other miracle material headlines that quietly disappear a year later. The process is scalable, and it happens in a single continuous step. The researchers aren't describing some delicate one-off lab trick that only works under perfect conditions. They built a bioreactor system, meaning the entire growth process can, in theory, be scaled up the same way breweries scale up fermentation, just with cellulose instead of alcohol as the end product. That single fact changes everything about how realistic this material actually is as a plastic replacement, a discovery that requires rare ingredients, extreme heat, or equipment that doesn't exist yet in any factory, usually stays trapped in a research paper forever. This one doesn't have that problem. The core inputs are bacteria and a nutrient source, both of which are cheap, abundant, and already produced at industrial scale in other biotechnology industries like brewing, fermentation, and biomanufacturing. The applications the researchers pointed to are broad on purpose. Structural materials for construction and manufacturing, thermal management systems for electronics that overheat, sustainable packaging that doesn't shed microplastics into food, textiles that don't rely on synthetic fibers, even green electronics and next-generation energy storage components, where a flexible, strong, heat-dissipating material could replace parts currently made from petroleum-based plastic and rare industrial composites. Rahman himself framed the long-term vision simply. He said the goal is for these bacterial cellulose sheets to become common enough to replace plastic across multiple industries at once, not just in one narrow niche product. That's a very different ambition than most biomaterial research. which usually settles for replacing a single item like a straw or a shopping bag. It also helps that the raw ingredient behind all of this isn't rare or geographically limited. Cellulose-producing bacteria don't need a specific climate, a specific crop, or years of growth like a forest does. They need a nutrient source and time, which means this process could theoretically be set up almost anywhere in the world, not just near a single supply chain in a single country. That's a major advantage over plant-based alternatives that depend on farmland, seasonal harvests, or one particular region having the right growing conditions. Asterisk, asterisk. The honest challenge is ahead. Asterisk, asterisk. None of this means plastic disappears next year. Growing a structural material with living bacteria at the volume the world currently consumes plastic, which again is over 430 million tons annually, is an enormous manufacturing challenge. Bioreactors need to be built at massive industrial scale. Production costs need to come down through repetition and engineering. Refinement, the same way solar panels and batteries became cheap only after years of manufacturing improvements. Not overnight, there are also open questions the research community will need to answer over the next few years. How does this material behave after 5 or 10 years of real-world use in a product? Not just a lab test. How does it perform under extreme humidity, saltwater exposure, or long-term UV light? How exactly does it behave once it's discarded? And how quickly does it break down safely without leaving problematic residue behind? These aren't reasons to dismiss the discovery. They're simply the next chapter that has to be written before bacterial cellulose shows up in the products you actually hold in your hands. But step back and look at what's actually been proven so far. A material grown from living bacteria, using no petroleum, tested at a strength that rivals some metals, with better heat performance than the baseline version, and a manufacturing method designed from day one with scalability in mind. That combination is rare enough that it's worth paying attention to, regardless of how long it takes to reach store shelves for 100 years. The world built its entire infrastructure assuming plastic would always be the cheapest, easiest option on the table. This research doesn't ask industries to sacrifice performance for sustainability. It's suggesting for the first time in a serious, peer-reviewed way that you might not have to choose between the two at all if this video gave you a new appreciation for something as invisible as bacteria. Quietly doing engineering work most of us never think about. Tap the like button and subscribe so you catch the next one. There are more videos like this one waiting on your screen right now. Here's something worth sitting with before you go. If the answer to one of the biggest pollution problems humanity has ever created was hiding inside a single-celled organism the entire time, what other solutions do you think are still sitting there unnoticed, waiting for someone to finally ask the right question?